Hi there, welcome to lecture 6 of Fox. Today's topic is strong induction. And if you remember, we just talked about induction, and induction is so important that Orange Malik gave the lecture. Well, induction is so important that it's even worth spending a second lecture on induction. Okay. Now let me remind you what we did last time. So last time we talked about induction. Okay, how do you prove for all? And we used the induction machinery, to prove that 4 to the n minus 1 is divisible by 3 for all n greater than or equal to 1. Something that might not have been obvious, but then we proved it with induction. Okay. And then we also proved that the sum of the first n integers is 1/2 n times n plus 1. It's a very famous sum. It's worth remembering that 1 plus 2 plus 3 up to n is equal to 1/2 n plus 1. It's quite amazing that we can get a closed formula for such a sum. We can also get a closed formula for the sum of the first n squares. And the sum of the first n squares is 1/6 n plus 1, 2n plus 1. Okay. And if you did what I asked you to do last time, and sort of read up in the book this method of differences, that's a systematic way of trying to get formulas that you might be able to prove with induction. Because one of the problems with induction is that it doesn't derive the formula for you to prove. It's a machinery for proving something once you have a guess, once you have a suspicion what the right result is. Okay. And lastly, last time I showed you that, pretty much anything you can prove with induction, you can prove with the well-ordering principle and contradiction. Okay. The so-called method of the smallest counterexample. Okay, the smallest counterexample approach. Okay. And so today, what's the plan? Since we already covered induction, it's just induction by osmosis. Induction. So we're going to start with some sort of slightly harder problem that uses induction to prove a fairly, esoteric-looking, tough inequality. Okay. And then I'm going to show you something peculiar about induction. And it's peculiar in general that, sometimes we try to prove something, we fail. And with induction, you might fail to prove something that's easy, but you might be able to succeed to prove something that's harder. And that's a very peculiar situation that occurs with induction. It's sometimes easier to prove harder things. Okay. So we'll show you examples of how this arises and why this arises, and then we'll consider many flavors of induction, leaping induction, and the ultimate sort of induction, strong induction. But I want to emphasize that all these other flavors of induction are no more powerful than the original induction that we discussed last lecture. In fact, they're all just derivatives of the original induction. So it's just that, just like, there's one way to prove an implication. Look at the truth table and argue that the true-false row doesn't occur. There's one induction, but there are many flavors, and sometimes if you use one of the flavors, it's a little easier to make a proof than if you use another flavor. But you can always prove anything with induction using the type of induction that we talked about last lecture. That type of induction is usually called ordinary induction. Today we're going to talk about strong induction. Oh wow, okay, what an exciting lecture we have in store for you. Okay, so let's get loads of practice with induction. We're going to start with a very daunting looking formula, inequality actually. So 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus and so on up to 1 over the square root of n, okay, is at most twice the square root of n. Okay. So you can think of this as an inequality involving n. So as with any induction, this is what's going to define our predicate, our P of n. So our P of n is the claim or the predicate that this inequality holds. So now we want to prove this by induction. Okay. So proof by induction. First step in any induction, base case. Okay, so the base case. Okay, and we want to make this claim for all n greater or equal to 1. So the base case is n equals 1. Okay, so P of 1. What does that claim? What it claims is that, 1 over square root of 1, so n equals 1. So you end the sum here. 1 over the square root of 1 is less equal to twice the square root of 1. So 1 over the square root of 1 is less equal to twice the square root of 1. And that means that 1 less equal to 2, which is clearly true. So clearly true. Okay, so we've established a base case, P of 1. Remember, I'll put up here a sort of a visual of what induction is doing. So induction establishes the infinite chain P of 1 implies P of 2, implies P of 3, implies and so on. An infinite chain, and then, so we need to establish the infinite chain, and we also need to prove the leftmost claim. So we need to prove P of 1. Okay, and then this P of 1 together with the infinite chain sets up an infinite cascade of inferences that allows us to conclude that P of n is true for all n. Okay, so that's the basics of induction. Okay, and here what we're doing is we're establishing the base case. We're establishing the leftmost claim in this infinite chain. Okay, and the next step in an induction proof is to actually prove that infinite claim. So that's called the induction step. And in this case, the induction step is to show that P of n implies P of n plus 1. Okay, so we get to assume, basically we're proving an implication, so we get to assume P of n is true. So assume P of n, which is the claim 1 over square root of 1 plus 1 over the square root of 2 plus all the way to plus 1 over the square root of n less equal to twice the square root of n. We get to assume that. And now we have to prove P of n plus 1. We only get to assume this in the induction step. So prove P of n plus 1, which is the claim that 1 over the square root of 1 plus 1 over the square root of 2 plus all the way to plus 1 over the square root of n plus 1 over the square root of n plus 1 less equal to twice the square root of n plus 1. Okay. This is the fundamental induction mechanics. Okay. And it's very good. You might not see exactly how to prove P of n plus 1 starting from P of n, but it's very important that you actually just know the mechanics. You should be able to set up the induction proof. Okay, now the creativity in an induction proof is to somehow figure out how to relate the claim that you're trying to prove to the claim that you can assume that you can assume to be true. And in this case, it's reasonably straightforward because we observe that this is a sum that includes this sum plus an additional term. So we know that 1 over square root of 1 plus 1 over the square root of 2 plus 1 over the square root of n is less equal to 2 square root of n. That we know. Okay? This is what's called the induction hypothesis. Okay? And if we add 1 over the square root of n to both sides, then we get 1 over the square root of n plus, all the way to plus 1 over the square root of n plus 1 over the square root of n plus 1 is less equal to 2 square root of n plus 1 over the square root of n plus 1, because I've added 1 over the square root of n plus 1 to both sides. Okay, and now this is where this induction proof gets hard. It's not the case that all induction proofs are just trivial and it's easy to prove this implication. Now we are wondering what the heck to do now. Okay, because this doesn't look anything like that. Okay, and indeed, there is no way to simplify this to get that. Even though we have the left-hand side, it's not easy to simplify this to get that. But we don't need this to equal that. Okay, we just need this to be less than or equal to that. So, question: is it true that the 2 square root of n plus 1 over the square root of n plus 1, 2 square root of n plus 1 over the square root of n plus 1 is less equal to 2 square root of n plus 1? Question mark. Turns out, yes. Okay. And let me prove it to you quickly. So, and I'm going to call it a lemma. So this introduces you to the concept of a lemma. It's still a claim. It's just that, it's not a claim that is important in and of itself. It just tells the reader, I'm about to prove a lemma. I'm about to prove a claim that I don't really care about so much. It's just that I need the claim. I need this lemma in order to prove something else. So lemma. Okay. For n greater equal to 1, it is the case that twice the square root of n plus 1 over the square root of n plus 1 less equal to twice the square root of n plus 1. Just claiming that as a side result. Okay. Now, proof by contradiction. So this is nice because it also gives us a little bit of practice with some other proof techniques, in this case, contradiction. So how does a proof by contradiction start? It starts by assuming that whatever you're trying to claim is false. So assume twice the square root of n plus 1 over the square root of n plus 1 is less equal to is greater than twice the square root of n plus 1. Now, Usually when you have, equations like this, it helps to simplify. And we can simplify by multiplying both sides by the square root of n plus 1. In this case, this becomes 1. The square root of n plus 1 times square root of n plus 1 is just n plus 1. And this becomes twice the square root of n times n plus 1. So, if we multiply by square root of n plus 1, we get twice the square root of n plus 1 is greater than twice n plus 1. Okay. If we subtract 1 from both sides, we have that twice the square root of n plus 1 is greater than 2n plus 2 minus 1. So 2n plus 1. Okay. And now squaring both sides again, we have that 4n plus 1 is greater than the square of this guy, which is 4n squared plus 4n plus 1. This is 4n squared plus 4n. 4n is greater than 4n squared plus 4n plus 1, or, if I cancel out the terms involving n, or 0 greater than 1. That is fishy. Okay, and technically we call it a contradiction, and that's the end of the proof. But the moment I come to something fishy, it means my starting assumption was wrong, and that means that my lemma, which is just a way of saying helper claim or helper theorem, just like we have helper functions when you program. This is a helper result. Okay, our lemma is proved. But by this lemma, it means that this guy here is less equal to, so this plus this, the lemma claims that this plus this is less equal to twice the square root of n plus 1. So, but look, this guy less equal to this guy, which is exactly what I wanted to prove. Okay. I wanted to prove that this ugly-looking complex sum is less equal to this. And that establishes the induction step, because this is what I needed to prove. Therefore, Pn plus 1 is true. Okay, and now we have established the induction step, we've established the base case. So by induction, okay, P of n is true for all n greater equal to 1. Okay? Hard induction proof. No problem. Okay. You can do hard proofs too. There's nothing wrong with that. Okay. So let me erase. Next, I want to show you something that's a little bit peculiar with induction. And I'll give you a hint at where we're going. What I want to show you is that with induction, sometimes it can be easier to prove a harder result than a harder, more complex result than the simpler, sort of easier looking result. Okay. Okay, so next problem. Let's prove that n squared is less than or equal to 2 to the n for n greater equal to 4. Okay. And this is to illustrate this concept that, a peculiar thing happens with induction, that sometimes something is easier to prove even though it's a stronger claim. Okay. So first thing, let's tinker. I want to show you why did we need n greater equal to 4. Okay, so let's put n equals 1, 2, 3, 4, 5, 6. Okay, so let's tinker. Okay, and let's look at n squared, and let's look at 2 to the n. Okay, so n squared is 1, 4, 9, 16, 25, 36. 2 to the n is 2. Okay, so 2 to the n is bigger, but then 2 to the n becomes 4. Okay, so still bigger equal to, and then 2 to the n is only 8. Okay, so it's less than. Okay, so it's not always bigger equal to n squared. It's not bigger equal to n squared for n greater equal to 1. Okay, but now at 4, 2 to the n, x is bigger equal to 16. It's actually equal to 16, so we get equality. So it's bigger equal to n squared. And then at 5, you get 32. At 6, you get 64. And now it turns out that it will always stay bigger. Are we sure it's going to always stay bigger? Are we sure n to the n will always stay bigger than n squared? Well, it turns out yes. And that's what we're going to prove with induction. So let's see how that works. Another inequality. Okay, so P of n is this claim. Okay, and we're claiming that this P of n holds for all n greater than or equal to 5. So let's for all n greater than or equal to 4. So this is going to illustrate a few new things. So proof by induction. Okay. So since we only need to prove it for n greater than or equal to 4, we only need our infinite chain to start at n equals to 4. Okay. So if we have an infinite chain of implications that starts at P of 4, and if we manage to prove this, then we've started the infinite cascade that's going to prove it. That's going to prove P of n for all n, on the right. Okay, i.e. for all n greater than or equal to 4, the infinite cascade of dominoes falling starts at n equals 4. So the first difference between this proof and all the proofs we've done so far is in the base case. Okay, so the base case. In this case, the base case starts at 4. So the base case is P of 4, which claims that 4 squared is less than or equal to 2 to the 4, and this is 16, and this is 16. So it's clearly true. Okay. And now let's continue. What do we continue with? The induction step. So it's always the same. This is the beauty of an induction proof. The proof mechanics is always the same. You have to prove a base case, you have to prove the induction step, and the induction step is always the same. You have to prove that P of n implies P of n plus 1 in a typical induction. Okay. And it may be tricky to prove, but the steps are always the same. So induction step. Okay. So what do we have to prove? We have to prove that P of n implies P of n plus 1. And again, a difference between this proof and all the proofs we've done before. We had to prove this implication for all n greater than or equal to 1. Now we don't. We only need to prove the implication P of 4 implies P of 5, P of 5 implies P of 6, and so on. So we only need to prove the implication for n greater than or equal to 4. So we have to prove this implication for all n greater than or equal to 4. Another difference. And that's related to the fact that the base case is only 4. We want to only show the claim for n greater than or equal to 4. Okay? So let's see how we'll go about doing this. Well, it's the usual story. In a proof of an implication, you can either use direct proof or contraposition. And the typical choice is direct proof. Okay? So we assume P of n. What is that? It's the claim that n squared is less than or equal to 2 to the n. And we want to prove P of n plus 1, which is the claim that n plus 1 squared is less than or equal to 2 to the n plus 1. Again, it's very important that you write down the claim P of n plus 1 because, it's easy to make mistakes in actually translating the claim P of n to P of n plus 1. And I'm just going to mention that you have to replace every instance of n in the claim for P of n. You have to replace every one of those instances with n plus 1 everywhere. Okay. All right. So let us see. We would like to make a claim about n plus 1 squared. So that's where we're going. So let's see what is n plus 1 squared. N plus 1 squared. Okay, now it's important. You cannot write down this claim as if it's true. But we're not going to write down that claim as if it's true. We're just analyzing n plus 1 squared. So everything we do has to be valid. And indeed, it is valid to say that n plus 1 squared is equal to n squared plus 2n plus 1. It's a valid step. Okay. Now, you observe that I have n squared here. Okay. Look, I got to assume that n squared is less than or equal to 2 to the n. So that means that this guy here is less than or equal to 2 to the n plus 2n plus 1. Okay. And it turns out that, unless we can, make some sort of non-trivial steps from this point, we're kind of stuck. Okay? Because we've certainly got, we're after this, but there's no easy way to see why this, should be either equal to that or less equal to that. Okay? Now, this is where you need a little bit more creativity. You kind of build a wish list. Okay, you say, well, what do I need to conclude that this is less equal to 2 to the n plus 1. And now we will observe that 2 to the n plus 1 is exactly equal to 2 times 2 to the n, which is exactly equal to 2 to the n plus 2 to the n. So I'm trying to prove that n plus 1 squared is less than or equal to 2 to the n plus 2 to the n. And here I've got n plus 1 squared is less equal to 2 to the n plus something else. And I would be done if this guy was less equal to 2 to the n. I would be done, because then I'd have 2 to the n plus 2 to the n, and I would be done. But, I didn't get to assume that. I only got to assume that n squared is less equal to 2 to the n. Okay? So what do I do now? Kind of trapped. Okay. And now I'm going to show you this interesting phenomenon with induction, which says that sometimes when you're trapped and you build this wish list of what you would like to be true, sometimes you can add that to the original claim that you were trying to do. Okay, the original claim that you were trying to prove was that n squared is less equal to 2 to the n. What if I make the original claim harder or stronger? Okay. Suppose instead I made the claim, let's call it now Q of n, which is the claim n squared is less equal to 2 to the n and 2n plus 1 less equal to 2 to the n. So that would certainly, solve my difficulties here. Okay. And let's compare this claim Q of n with this claim P of n. Well, P of n is the claim n squared is less equal to 2 to the n. Q of n is the claim n squared is less equal to 2 to the n and something else. So I have to prove two things here. Okay. And now here's the peculiarity. I'm going to go and prove those two things. Okay. And it's going to be easy to prove those two things. But it's much harder. Well, not much harder, but it's harder to prove the original claim. And you say, whoa. How is that possible? How is it possible that it's going to be easier to prove this quote-unquote stronger claim when we already had difficulty proving the easier claim? So, that's the peculiarity with induction, and, the high-level reason for why it can be harder to prove, why it can be easier to prove a harder claim is, the main sort of difficult step in an induction is usually the induction step, where you have to prove an implication. So it's true. You have to prove something harder. Okay? But you get to assume what's on the left-hand side here. Okay? So you get to assume more. So you get to assume more, and you have to prove more. Okay? If you're trying to prove something harder. Okay? And sometimes the little bit extra that you get to assume is enough to allow you to prove that little bit more. Okay. And we're going to see that in action here. So, it's a little bit scary. I couldn't prove this guy, okay, but I'm going to prove more here. And why do I say this is stronger? Because if Q of n is true, then certainly P of n is true. Certainly. Okay. Because, Q of n involves P of n and something else. So if this is true, then this and that are true. So this is certainly true. Okay, so let's prove this harder claim by induction. Proof. Okay, proof. So, by induction. So, the base case. Again, we're interested in n greater equal to 4, so we need to prove Q of 4. Okay, well, what's that? That's the claim that, 4 squared is less equal to 2 to the 4, which we know is true. And 2 times 4 plus 1, so 2 times 4 plus 1 is less equal to 2 to the 4. So this is 16, and this is 9, and so that's also true. So we've proved the base case. Interesting. Okay. So the conclusion is that Q of 4 is true. Now the induction step. Okay. It's the same induction step. The only difference, the only thing that's changed is I have a new claim, which is a stronger claim. It's just Q. So we're proving Q, not P. So the induction step is I have to prove Q of n implies Q of n plus 1 for all n greater or equal to 4. So I get to assume, what do I get to assume? I get to assume Q of n. So I get to assume that n squared is less or equal to 2 to the n, and 2n plus 1 is less or equal to 2 to the n. Now I need to prove Q of n plus 1. And this is where I said that, you need to be careful when you write down what is the claim Q of n plus 1. So you need to substitute n plus 1 for n in every instance of n here. So this is the claim, n plus 1 squared is less or equal to 2 to the n, and, 2 to the n plus 1, and now I have to replace this n here by n plus 1. So I get 2 times n plus 1, okay, which is 2n plus 2. So and then 2n plus 2 plus 1 is 2n plus 3. So I have to prove that, n plus 1 squared is less equal to 2 to the n plus 1, and 2n plus 3 is less equal to 2 to the n plus 1. That's what I have to prove for the induction with Q of n. Okay, so let's go ahead and do it. So I need to prove this. So I need to prove that n plus 1 squared less equal to 2 to the n plus 1. n plus 1 squared is equal to n squared plus 2n plus 1. But that's no problem, because n squared is less equal to 2 to the n, and 2n plus 1 is less equal to 2 to the n. And I got to assume that because I can make those claims because I assumed this and. So this is true and that is true. So this is less equal to 2 to the n, and that is less equal to 2 to the n. So this is less equal to, so here we have less equal to 2 to the n, and here we have less equal to 2 to the n. So the whole thing is less equal to 2 to the n plus 2 to the n, which is 2 times 2 to the n, which is 2 to the n plus 1. So I have proved this. So you see, even though I'm technically trying to prove something harder, this at least this part of the induction step was much easier than trying to prove it here somehow. Okay, because I got to assume more. I got to assume both this guy and that guy. That's what made this proof go through. I got to assume more in the proof. Okay, am I done? No, because I have to prove Q of n plus 1, which is an and. Okay, here I only had to prove P of n plus 1. Here I have to prove Q of n plus 1. And that is the price you pay in the induction for getting to assume more. You also have to prove more. So I not only have to prove this guy, I have to prove that guy as well. So I have to prove that 2n plus 3 is less than or equal to something. But 2n plus 3 is equal to 2n plus 1 plus 2. Okay. And look, 2n plus 1. I from my assumption, from my induction hypothesis, I have that 2n plus 1 is less equal to 2 to the n. So this is less equal to 2 to the n. Well, and this is 2, which is certainly less equal to 2 to the n when n is bigger than or equal to 4. So this is certainly less than or equal to 2 to the n. So this is less equal to 2 to the n plus 2 to the n, which is 2 to the n plus 1, as required. So I've proved that. So I have proved Qn plus 1. Proved Qn plus 1. So therefore, Q of n plus 1 is true. And that's the induction step. I proved that Qn implies Qn plus 1. And so therefore, by induction, I'm done. By induction, Q of n is true for all n greater or equal to 4. Okay. And why 4? Because I only proved this implication for n greater or equal to 4, and my base case was 4, was n equals to 4. Okay, so let me summarize. This is kind of stunning. Okay. I tried to prove something, and somewhere along the way, in the induction step, I got stuck. I make a wish list. It would have been nice if I got to assume that this is less than or equal to 2 to the n. And that wish list, I have to add to the claim. Okay, so then I came up with a claim that was stronger, a stronger claim. But somehow, miraculously, and this is the peculiarity with induction, somehow this stronger claim became easier to prove. Okay. And let's see exactly how that happened. Okay, how did that happen? Well, in this stronger claim, what I got to assume was two things. I got to assume this stronger claim for n. Okay, I got to assume, n squared is less equal to 2 to the n, and I got to assume this part. Okay, and being able to assume that part allowed essentially this step to go through. Okay, it allowed me to conclude that n plus 1 squared is less equal to 2 to the n plus 1 effortlessly. Okay, so as expected, that wish list, adding this into the induction claim into the induction hypothesis, helped me to get this step through without any effort. But then there was a price to pay. That's not all I have to prove. Okay? I have to prove the added step. That's the price I have to pay. This added part that I added to the claim, I have to prove that as well. Okay? So I had to prove that, but that turned out to be not so hard. Okay? So in an induction, when you're trying to prove an implication, and that's the beauty of implications, it can be easier to prove a harder implication in the induction step. And that's because, when proving an implication, you get to assume this, you have to prove this. Okay? And it is true that the claim is harder. So that means that what you have to prove is more, but you also get to assume more. And if you balance that just right, if you balance what you get to assume with what you have to prove, that's when the induction works effortlessly. Okay? So there. Summary. Sometimes with induction, and this can also happen in other kinds of problems and other kinds of proofs that you'd like to do, but sometimes with induction, it is easier to prove something that's stronger because of this balancing act that goes on between what you get to assume and what you have to prove in the induction step. The base case will always be harder, because in the base case we had to prove more as well. But when you're proving the base case, you don't get to assume anything. It's the induction step that gets hard, that gets easier, that can get easier when you have a harder claim to prove, a stronger claim to prove. And that is something that's somewhat unusual with respect to induction. Okay, so let's erase. Let's get back and do more examples. By the way, so this is the original claim, and it follows from Q of n. And here is the strengthened claim. Sometimes we refer to that as strengthening the induction hypothesis, because in the induction hypothesis, we got to assume more. So we strengthened that. We gave ourselves a base from which to move that's stronger, and it allowed us to prove that stronger thing for n plus 1. So this is sometimes called strengthening the induction hypothesis. Speed erase. Yeah. Boom. Okay, so let's do another example, and just to show you that induction is very powerful. We can use it to prove all kinds of things, not just formulas. Okay. And so we're going to go into L-tile land. L-tile land. Okay. So what's an L-tile? So think of like a Tetris tile, but not a Tetris tile. So, that's an L tile. Three grid squares in the shape of an L. Okay, and think that you can rotate, flip, whatever you want. Okay, so you can rotate this thing around, and the goal is we're going to look at some grids. Okay, and we're going to ask whether they can be tiled using L tiles. Okay, so let's start small. So in other words, let's tinker a little bit and let's look at the 2x2 grid. So this is the 2x2 grid. So this is 2x2. Okay, and imagine that on one of these squares, I'm going to remove one of these squares. Let's say I want to grow a tree there, and the rest of this patio I want to tile. So I'm going to remove a center square. There's no real center square, so I'm going to remove this square. Okay, and I can grow a tree there, and I need to tile this, and no problem. Okay, I can just place a tile here, and that's an L tile. I rotate it this way, and I can place it here. So I can tile the 2 by 2 grid after removing one square. Okay. Let's look at the 4 by 4 grid. So similar situation. Let me just draw the 4 by 4 grid. Okay. Okay. And again, I'm going to remove one of the center squares. Again, there are 4 center squares, but I'll remove one of them. Okay. So let me remove one of these. And now is the interesting question. Is it possible to tile what remains, the patio that remains, with L tiles? And yes, and let's see how we can do it. Okay, so what I'll do is I'll place one tile here. Okay, look at how beautifully I can color tiles. Feel a little bit like Bob Ross here. Okay, now what do? Well, I have to tile the rest, so let me place a green L here. I'm just using different colors. It's not that the tiles have different colors. I'm just using different colors so that you can see. Okay, so I'll place a green one here. Okay, no problem. Okay, and then I'll place a red one here. Again, no problem. Okay, I'll place another red one here. And you can see that I'm going to be able to complete the tiling. Okay, with one more tile here. Let me make it green. Look at this beautiful picture. Wow. Okay, now make this green. Okay. So this is the 4 by 4 grid. And we can ask, can we do this for the 8 by 8 grid? So you see the idea here. This is 2 to the 1 by 2 to the 1. This is 2 to the 2 by 2 to the 2. So the next, the next grid in this progression. And there are other grids we could ask, can we tile? But for the moment, I'm looking at powers of 2. Okay. So let me draw the 8 by 8 grid. Okay. And 8 by 8 grid. Look at this. You can draw with me. Look at how beautifully I draw grids. Okay, so there's the 8 by 8 grid. And I'm going to take one of these center squares and, remove them. Just one. Okay. So, they started out with 64 squares. I removed one, so that's 63. And the L tile has 3 squares, and it's a good thing that 63 is divisible by 3. So this is the 2 to the 3 by 2 to the 3 grid. Okay, so 8 by 8. Okay, now, can we tile this? Okay, now I'm going to show you the idea, okay, but you can go ahead and complete the tiling. I claim yes, and the way I'm going to start this tiling is I'm going to observe that this 8 by 8 grid is actually 4 by 4 grids. So I'm going to draw a line here and a line here. Okay, so I've decomposed this 8 by 8 grid into 4 by 4 grids, and I observed that this center square will be in one of these 4 by 4 grids. And so what I'm going to do is I'm going to place an L tile. Okay, I'm going to place one L tile to cover the 3 squares that are in the other 4 by 4 grids. Okay, so I'll place one tile in here so that it covers a square in each of the 4 by 4 grids. Okay. And now you see that I've got 4 similar looking 4 by 4 grids, and if I can tile, each of them, then I will accomplish a tiling of the entire 8 by 8 grid minus 1. Okay. And that's the idea behind how I'm going to solve the problem for 8 by 8. And this, so if I can solve the problem for this 4 by 4, then I can solve the problem for the 8 by 8. And that's the essence of induction. That if you can solve the problem if you can solve your task for a smaller instance of the problem, then you can show that you can solve it for the larger instance. That's the basic idea behind the sort of induction step. The P of n implies P of n plus 1. Okay, so here's P of n, and that implies P of n plus 1. Think of this as smaller problem. Okay, and if you can show that this is true, then think of this as the larger problem. So if it's true for the smaller problem, then it's true for the larger problem. That's sort of like saying, if I can solve it for the smaller problem, I can solve it for the larger problem. Okay? And that's the basic idea behind induction. Okay? And so I claim that no matter what n is, the 2 to the n by 2 to the n grid minus a center square can be tiled with L tiles. So claim P of n, the 2 to the n by 2 to the n grid minus a center square can be L tiled. Okay, now why do I say a center square? Because actually there are 4 center squares in any such grid. Okay, and so you can pull out any one of those center squares and you can tile it. Okay, so let's prove this by induction. Proof by induction. Okay, and it's going to now once we decide to prove it by induction. So let me emphasize: a proof by induction may or may not work. Okay, but once we decide to prove it by induction, the mechanics is very straightforward. It's always the same. So first step, base case. Step 1, base case. So when n equals 1, so P of 1, the 2 to the 1 by 2 to the 1 grid minus a center square can be L tiled. So we just showed this here. Actually, there are 4 different center squares you could remove, and each of them can be L tiled. So the base case we verified. Okay, is P of 1 is true. We verified it. Okay. This is the basic idea behind induction. The mechanics is always the same. Induction step. I induct step. So now we need to prove P of n implies P of n plus 1. Okay. And so we've proved this implication. So we assume, we're going to use a direct proof. So assume P of n, this is the very standard induction template with a direct proof of the implication. Assume P of n, what does that assume? It assumes that the 2 to the n by 2 to the n grid minus a center square is L tileable. Okay. And now we have to show or prove P of n plus 1. So this is the induction mechanics. So we have to prove P of n plus 1. What is P of n plus 1? So it states that the 2 to the n plus 1 by 2 to the n plus 1 grid, minus a center square is L tileable. Okay? And so how do we prove this? Well, we're going to use this basic idea that I illustrated, and hopefully you'll go and now tile the remaining 4 by 4 squares in a similar way to how we tile this. Okay, slightly different. Okay, but we're going to use this basic idea that, when you move from n to n plus 1, so 2 to the n goes to 2 to the n plus 1, it multiplies each dimension by 2. So, it basically, if you have the 2 to the n by 2 to the n square, so here's the 2 to the n by 2 to the n square, 2 to the n by 2 to the n. then 2 to the n plus 1 by 2 to the n plus 1 simply adds another square here on each dimension because it's doubling. Okay, so now this is 2 to the n, this is 2 to the n, and so this together is 2 to the n plus 1. This together is 2 to the n plus 1. Okay, so that's what the 2 to the n plus 1 by 2 to the n plus 1 square looks like. It's composed of 4 2 to the n by 2 to the n squares. Okay, and now we're removing the center square. So this guy is removed. Okay, and we ask whether we can L-tile this. Okay, so I'm going to use this idea. Okay, I'm going to place one L-tile here. Okay, so I'll place one L-tile here. Okay. And now it would be great if I could somehow use the induction hypothesis, which I was able to assume, to L-tile each of these these 2 to the n by 2 to the n squares independently. Okay. And the problem is I cannot. Okay. The problem is so it is indeed the case that this is a 2 to the n by 2 to the n square that's missing. So it's a 2 to the n by 2 to the n grid that's missing a square. So this is a 2 to the n by 2 to the n grid that is missing a square. Okay. But P of n does not allow me to conclude that I can L-tile it. But P of n does not allow me to conclude I can L-tile. And the interesting question is why? Okay, why? Okay. So now this is important. Okay. So the whole idea in an induction is to somehow be able to use your assumption to help you to prove the higher case, the P of n plus 1 case. Okay. So we have to look very carefully at our induction hypothesis, our assumption. Okay. And what does the assumption say? The assumption says very clearly that the 2 to the n by 2 to the n grid minus a center square can be L-tiled. The problem here is that this 2 to the n by 2 to the n grid is missing a square, but it's not a center square, it's a corner square. And that's the same with all of these guys. They're all missing not center squares, they're all missing corner squares. So we cannot use the P to the n assumption to tile that, because it's not this grid. This smaller grid is not of the form to which we can apply P to the n, P of n. Okay, but now let's remember back to the other problem where we were trying to prove something and then we got to a point and the induction hypothesis alone wasn't enough to allow us to conclude that P of n plus 1 was true. So we said, well, let's build a wish list. What else would we like to be true? So we would like not only that you can L-tile the grid if it's missing a center square, but we would also like that you can tile the grid if it's missing a corner square. Okay? So let's prove the stronger claim that I can L-tile a 2 to the n by 2 to the n grid if it's missing a center square or a corner square. That's stronger because it's two things. Okay? But that's what I need to make this go through. And hopefully by proving this stronger claim, I can balance what I get to assume with what I need to prove and prove everything. Okay? And indeed that's the case. And let's now go through the proof of this stronger claim. So this is another example where, this peculiar thing with induction occurs where, I'm trying to prove something I cannot. Okay? And I see something else that I need, kind of like a wish list. Okay? So let's add it into the claim. Let's make the claim stronger by adding my wish list into the claim. Okay? So, stronger claim. Okay. The 2 to the n by 2 to the n grid minus a center square can be L-tile, and the 2 to the n by 2 to the n grid minus a corner square can be L-tile. You see, I'm adding something more to prove, not just that if it's missing a center square it can be L-tile, but also if it's missing a corner square it can be L-tile. Okay, so instead of calling this P of n, let's call it Q of n. A new predicate, just not to confuse it with the original one. I want to emphasize it's a stronger claim because it's an and. I have to prove two things. And if Q of n is true, then that immediately tells you that P of n is true, because this is including, the center square case as, one of its claims. Okay? And it turns out that this we can prove with induction. Okay? So let's go through that proof now very quickly. Okay, so the proof is exactly the same. The mechanics is exactly the same, and I'm going to emphasize that by just leaving the sort of infrastructure, the scaffolding of the proof intact. I'm just going to erase the P of n part, and we're going to replace that with Q of n. So this stuff, so the mechanics of the induction proof stay the same. Okay? And let me erase this picture, and we'll put a new picture on. Okay, so induction step. So the proof by induction of Q of n. So we need the base case, which is Q of 1. Q of 1. Okay. The 2 to the 1 by 2 to the 1 grid. 2 to the 1 by 2 to the 1 grid. Missing center or corner square is L-tileable. Well, the 2 by 2 grid, the center and corner squares are all the same. If you take out the center square, that's the same as a corner square. There's no difference. Okay. And if you feel like tinkering a little more, go and see if in the 4 by 4 grid, if I remove a corner square, can I L-tile? And you can see that it'll clearly be the case, because if I remove this square, all I do is place this red L-tile over here. Okay, and I've got this box, and then everything else stays the same. Okay, so the 4 by 4 can be done. Okay, so we've verified more than just the base case, but that's okay. It's perfectly fine to tinker a little more than you need to. What's not fine is to tinker less than you need to. Okay, now induction step. Assume Q of n. Okay, what does that mean? The 2 to the n by 2 to the n grid missing a center or corner square is L-tileable. Okay? So that's what we get to assume, that if you have the 2 to the n by 2 to the n grid, and if it's missing a center or a corner square, we can L-tile it. Now we need to prove Q of n plus 1. That is the 2 to the n plus 1 by 2 to the n plus 1 grid, missing the center or corner square is L-tileable. Okay? So, important. We get to assume more, but we also have to prove two things. And that might look hard. Okay? But it turns out in this case, the induction hypothesis is enough to prove these two things. So it's a case of you need to balance when making a claim, the strength of the claim should be such that what you get to assume balances what you get to prove. Okay, so you get to assume enough to prove what you need. Okay. All right, let's prove it. Well, there are two things to prove. So let's consider the bigger grid, which is twice as big. Okay. So here we have 2 to the n, 2 to the n, 2 to the n, 2 to the n, and it's missing a center square. Okay, no problem. And it could be missing any center square. The argument is basically the same, because all the center squares being removed are equivalent, because you can just rotate the grid. Okay, and the second case we need to prove is that what if you've taken out a corner square? Okay, so you've taken out a corner square. Okay, so again, this is the 2 to the n plus 1 grid, so it's 2 to the n, 2 to the n, 2 to the n, 2 to the n. So that gives you the 2 to the n plus 1 grid. But now you've not taken out a center square. We need to prove two things now because we've got a stronger claim. Here we've taken out a corner square. Okay, so what I need to show is that both of these can be L-tiled. Okay, and okay, you might say, well, what about if I take out that corner square? Just rotate it and it becomes this corner square. It's that corner square, just rotate it and it becomes the top left corner square. So sometimes people say, without loss of generality, assume that the corner square that's removed is at the top left. And we can say, without loss of generality, assume that the center square that has been removed is in the top left quadrant. Okay? So, here's the basic idea. Place an L-tile here. Okay, so that it occupies the three 2 to the n by 2 to the n grids that do not have a missing square. Okay. Now, I have 4 2 to the n by 2 to the n grids, and each of them is missing a corner square. But I know that that can be L-tiled by the induction hypothesis, because the induction hypothesis says 2 to the n by 2 to the n missing a corner square is L-tileable, no problem. So, this can be L-tiled on its own. This can be L-tiled on its own. This can be L-tiled on its own, and this can be L-tiled on its own. So that means the whole thing can be L-tiled by just, using the independent L-tilings of each subgrid. What about this guy? Same idea. Okay, place an L-tile right here, occupying the three grids that have not got a square missing. Okay, that effectively removes one square from each grid. So now each of these grids, okay, so this grid is a 2 to the n by 2 to the n grid missing a corner square. And this grid is a 2 to the n by 2 to the n grid missing a corner square, so they're all missing a corner square. So this grid can be independently tiled because we got to assume it. We got to assume that if you're missing a corner square, it's L-tileable. This is L-tileable. 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 So that means that the 2 to the n plus 1 by 2 to the n plus 1 grid, if it's missing a center square or if it's missing a corner square, in either case, you can L-tile. And that proves Q of n plus 1. So Q of n plus 1 is true. That's the end of the induction. Therefore, by induction, Q of n is true for all n greater or equal to 1. That's the end of the proof. By the way, for this particular example, you might think that this is a much stronger claim than what we originally had, because we originally wanted to prove it for center squares, but now we proved it for center squares and corner squares. It turns out that we can prove a much stronger claim, and it's just as easy to prove by induction. So let me call this R of n. Okay, and you can now sit down and try to prove this. And that's just an exercise. A 2 to the n by 2 to the n grid missing any square is L-tileable. L-tileable. Okay, that is hyperstrength. Okay, what could be stronger as a claim than that? You can take out not just a center square, not just a corner square, you can take out any square you want, and it can be L-tiled. Any square you want. Wow. Prove it by induction. Okay. Meanwhile, let's do the speed erase and keep going with examples. Induction by osmosis. Okay, another quick example before we get to strong induction. So consider n cubed versus 2 to the n. And I claim that n cubed is less equal to 2 to the n for all n greater equal to 10. Okay, so now if we were proving this with induction, we would have the base case, which is p of 10. So this is the base. P of 10, which claims that 10 cubed is less than 2 to the 10. This is 1,000. This is 1024. Okay, and clearly true, so check. Okay, now, in the induction step, we assume, P of n. So we assume P of n, so this is P of n. We assume P of n, which is n cubed less than 2 to the n. And it turns out that now we want to prove P of n plus 1, which is that n plus 1 cubed should be less than 2 to the n plus 1. In this case, it turns out to be much easier to prove n plus 2 cubed is less equal to 2 to the n plus 2. Okay, so watch. So n plus 2 cubed is equal to n cubed plus 6n squared plus 12n plus 8. Okay, and since n is bigger equal to 10, okay, so this is certainly, so 6 is less equal to n. So this is less, 6 is less than n. So this is less than n cubed plus n times n squared, because 6 is less than n. So 6 is less than n. 12 is less than n squared, because n squared is at least 100. And 8 is certainly less than n cubed, because n cubed is 1,000. So 6 is less than n, plus 12, which is less than n squared, so n squared times n, plus 8, which is less than n cubed. Okay, so this is equal to 4n cubed. And if we've assumed that n cubed is less than 2 to the n, this means that this is less than 4 times 2 to the n times 4, which is equal to 2 to the n plus 2. And that's exactly the claim P of n plus 2. So what we've proved here, okay, is that we've proved P of n implies P of n plus 2. Okay, but that's not what induction says. Okay, but it's not so bad, because let me show you the implications that we proved. We have P of 10, P of 11, P of 12, P of 13, and so on. Okay, let's put a few more. P of 14, P of 15, and okay. And what we've proved is that P of 10, let's put in P of 16, and P of 17, and so on. Okay, so P of 10 we proved implies P of 12. Okay, and implies n plus 2. P of 12 implies P of 14. P of 14 implies P of 16, and so on. Okay, that's what we've proved. And then the base case, P of 10 is true, allows us to has established that this is true. So it's not the cascade that we wanted, but we do have an infinite cascade. We've therefore established P of 12. Okay, and we've therefore established P of 14. And therefore we've established P of 16. And the cascade goes on, but you observe that the cascade is skipping over the odd numbers. So you can think of this P of n implies P of n plus 2 as a leaping implication. So this is a leaping implication. But still there are infinitely many of them, and the base case does indeed set up a cascade, set up a chain reaction of implications where we can conclude that P is true for all even numbers. Okay. Well, what about the odds? Well, it turns out that in here is embedded all the implications for the odd numbers as well. So it is the case that P of 11 implies P of 13, which implies P of 15, which implies P of 17, and so on. Okay. So those implication links have been proved. It's just that they're of no use to us because we haven't established P of 11. But if we do establish P of 11, okay, then we get P of 13, we get P of 15, we get P of 17, and so on. Wonderful. So, instead of one infinite chain, we have two separate infinite chains. Okay? So, that's not a big deal. If you have two rows of dominoes, okay, and you want all the dominoes to fall, you just need to tip the first domino in each of your rows. Okay, same thing here. You have two sort of interleaved leaping implication chains. If you want to topple all the implications, you need to just have one extra base case. And so in this case, when you prove the leaping implication, you just need to add one extra base case, P of 11. Okay, and what is that claiming? That 11 cubed is less than 2 to the 11. and I leave it to you to verify that indeed, P of 11 is true. And so this sets up the base cases that we need for both independent infinite chains of leaping implications to have a cascade, a chain reaction of true implications. And so one chain reaction establishes for the evens, the other for the odds. Okay, beautiful. Okay, let me show you an application. Let's go with 3 and 4 cent stamps. 3 cent and 4 cent stamps. Okay, so if you can make postage with 3 and 4 cent stamps, so P of n, let's define the claim P of n. You can make postage with of n, so postage of n with 3 cent and 4 cent stamps. Okay. Well, if you can make postage of n with 3 cent and 4 cent stamp, then there's an immediate leaping implication that says you can make n plus 3. Because, why? Because you just add a 3 cent stamp to n. So P of n implies P of n plus 1. Okay? And if P of n implies P of n plus 1, P of n implies P of n plus 3, okay, then we've set up now, unlike in this case where we had 2 independent chains, here we'll have a chain going from, from n to n plus 3. Okay, so we'll have, for example, we can do 6, we can do 7, and we can do 8. Okay, so we have P of 6, P of 7, P of 8. Okay, 6 gets you to 9. 9 gets you to 12. 12 gets you to 15. Okay, and so on. 7 gets you to 10. 10 gets you to 13. 13 gets you to 16. And then 8 gets you to 11. 11 gets you to 14. 14 gets you to 17. And so on. Okay, so now we have 3 independent chains. And so the only difference between this case and the previous case is, we have 3 base cases. And indeed you can do 6, 7, and 8, 3, 3, 3, 4, 4, 4. And so leaping induction, which is what this technique is, we're going to call this technique, leaping induction establishes it for all n. Okay? So this is just to show you that, in the regular case, we prove the link P of n implies P of n plus 1. This is regular induction. Okay, but the general idea of induction is if you can prove, the claim for n implies the claim for some higher n. So P of n implies P of n plus k. That's almost as good as regular induction. In regular induction, you have one base case. Leaping induction, so we say that this is a leaping implication if k is bigger than 1 because it leaps over. So P of n implies P of n plus 2, leaps over n plus 1 and implies n plus 2. So in this case, you will have k base cases. Okay, and this is a generalization of this. This and this are equivalent when k is 1. Okay, so just to show you another flavor of induction, which is called leaping induction. So let's erase. Okay, so I want to tell you about now strong induction. Strong induction. And I'm going to tell you about strong induction in the context of what I call representation theorems. Forget about the big word. Basically, I'm going to tell you mostly about the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic. Okay. So take any number. Let's say, for example, 36. So 36 is equal to 2 times 2 times 3 times 3. Okay. And what you will observe is that this is, a natural number, okay, bigger than 2. So natural number greater than or equal to 2. And what you'll observe is that I've written it entirely as a product of primes. Okay, and that's fundamental. So it's called the fundamental theorem of arithmetic. Basically, the prime numbers are the atomic units for the integers. In other words, every integer, every natural number bigger than or equal to 2 is either a prime or it can be represented as a product of primes. It's made up of primes. Okay? And the fundamental theorem of arithmetic goes one step further and says that, once you've represented it as a product of primes, basically it's unique up to reordering. So the fundamental theorem of arithmetic basically has two parts. So part 1, every n greater or equal to 2 is either prime or a product of primes. Okay, and this is an example of writing 36 as a product of primes. And the second part is that this product of primes is unique up to reordering. So the product of primes, so the primes that appear in the product is unique, up to reordering. I mean, we don't care that you could also write it as, 3 times 2 times 2 times 3, up to reordering. Okay, this is this absolutely fundamental theorem. Fundamental. Okay. So we're going to, in some way, shape, or form, we're going to prove this theorem, and we're going to prove it in 2 steps. Okay. And today we're going to prove the first step. Okay. Later on, when we do number theory, we'll prove the second step. Okay. And to prove the first step, it's a beautiful application of induction, in particular, strong induction. Okay. So, what is strong induction? So in order to sort of get to strong induction, let's see a little bit more what's going on with induction. So in induction, you prove P of 1. Okay? So you prove P of 1. So let me put it as, a check mark. Okay? And then you use P of 1 to infer P of 2 because you've proved the link P of 1 implies P of 2. Okay, so you prove the link P of 1 implies P of 2. Okay? And so you can infer P of 2. Okay? Okay? You can infer it because you proved the link P of 1 implies P of 2. Okay. Now, let's see what happens when it comes time to infer P of 3. Okay. Well, what link are we going to use? What link we're going to use is the P of 2 implies P of 3 link. Okay, so we're going to use the P of 2 implies P of 3 link. And because P of 2 is true, we can infer P of 3. Okay, so we infer P of 3. Okay. And then, what are we going to do when to get P of 4? We're going to use the link P of 3 implies P of 4. Okay, and we're going to infer P of 4. But now I want to point out something. What am I going to point out here? What I'm going to point out here is that when it is time to infer P of 4, we know at that point that 1, 2, and 3 are all true. Okay? So, we don't, so this link would certainly imply P of 4. Okay? This link would certainly imply P of 4. But, a weaker link would also imply P of 4. The following link would also imply P of 4. P of 1 and P of 2 and P of 3 implies P of 4. Okay? So if we have proved this link instead of this link, so the induction, or normal induction proves this link. Okay? But suppose, just imagine that instead of proving this link, we have proved this link, that P of 1, 2, and 3 implies P of 4. Would we be able to conclude P of 4? And the answer is yes. Why? Because look, we know that P of 1 is true, P of 2 is true, P of 3 is true. At the time that we come to prove P of 4, we know that all these are true, and if all of these are true, then the AND is true. If the left-hand side is true, we can infer the right-hand side. So this implication link allows us to conclude P of 4, but so does this implication link. So it suffices to prove this implication link. Okay. Now, which of these two implication links is easier to prove? Okay. It's much easier to prove this implication link. Much easier to prove. And why is that? Because let's look at the proof. Okay, to prove this implication link, we assume P of 3. Okay, and we prove P of 4. Okay, that's to prove, let's call this star. So this is star. That's how we prove star. Okay, prove star. Let's call this star star. Okay, to prove star star, okay, what do we do? Well, we're going to use, let's say we use a direct proof. We assume P of 1 and P of 2 and P of 3. So we assume P of 1, P of 2, and P of 3. And what do we have to prove? We have to prove, it's an implication, so it's a standard implication proof. We have to prove P of 4. So look at that. Okay. Over here, I get to assume P of 3 and I must prove P of 4. Over here, I get to assume more. Gives me more firepower. I get to assume P of 1, P of 2, and P of 3. Okay. And all I have to prove is the same thing, P of 4. So this must be easier to prove because I have way more firepower. Okay. All right. So, conclusion. It's much easier to prove this implication than that implication. Okay. And both of these implications will allow me to conclude P of 4. So if both of these implications would allow me to conclude P of 4, then I much rather prove the easier implication that will allow me to conclude P of 4. Okay? And that's just as valid an induction, because when we are doing the induction, it is indeed the case that everything up to that point has been proved true. Okay. So, what I'm saying, in a nutshell, is that in the induction step, so in the base case, you prove P of 1. And now I'm suggesting another induction step, which is an easier induction step, but allows us to get this infinite cascade of implications that we need. Okay? In the induction step, instead of, before it was P of 1 implies P of n plus 1. P of n implies P of, before it was P of n implies P of n plus 1. That was the old induction step. I'm suggesting a new induction step, which is, P of 1 and P of 2 and all the way up to and P of n. So, prove a much, easier to prove implication, which is that P of 1 and 2 and 3 and 4 and all the way up to n, they're all true. Okay? You can prove that if all of these are true, then I can conclude n plus 1. And that corresponds to this logic that, and this is enough because we know that everything up to 4 is true. Okay? And since everything up to 4 is true and we prove this implication, it means 4 is true. But then once we have 4, everything up to 5 is true. So we can conclude 5 is true. And that infinite chain of dominoes, that cascade of implications is the same as before. But now, this is much easier to prove. Induction step. Okay. Let me put this on a formal footing. Okay, on a formal footing. So I don't want to just, pull this over to you and say, here, take my word for it. Okay. So let me now prove to you that this is basically induction, but with a much stronger claim. This idea this idea is just induction with a much stronger claim. Okay. And if I want to prove P of n, okay, let me define a much stronger claim, Q of n, which is equal to the claim that P of 1 is true and P of 2 is true and P of 3 is true and all the way to and P of n is true. Okay, let me define this much stronger claim. Why is it much stronger? Because look, this is just the claim P of n. This is making the claim that not only is P of n true, but all the way up to P of 1 is true. 1 all the way up to n is true. This is a much stronger claim. Okay. Now, let's see how we would prove Q of n by induction. So, if I prove Q of n by induction, I've certainly proved P of n, because Q of n is much stronger than P of n. So, prove Q of n by induction. Okay. How do I prove Q of n by induction? I need to have a base case. Base case. Q of 1. Okay. Which is just the claim P of 1. Which is just the claim, same as P of 1. Okay. Induction step. Assume Q of n. What do I get to assume? P of 1 and P of 2 and all the way up to and P of n. Okay. Remember, this was the idea that we just discussed, that at the time, when you come to sort of trying to infer n plus 1, P of n plus 1, you know that 1 to n are all true. So Q of n assumes that, but this is just the standard mechanics for proving Q of n. You assume Q of n. Okay. Prove Q of n plus 1. What is that? Prove that P of 1 and P of 2 and P of n and P of n plus 1 are all true. Now it's not looking like induction anymore. Okay? Didn't you just say I have to prove only P of n plus 1? Okay? It looks like I have to prove all of this, but wait a minute. Yes, you do. You have to prove all of this, but this whole left part came for free. Because you assume that 1, 2 up to n are all true. So 1, 2 up to n are all true. So P of 1, P of 2, all the way up to P of n came for free from the induction hypothesis. Okay. So the only thing you need to prove is P of n plus 1. So only need to prove P of n plus 1. Okay. And then now that justifies the method that I just described. Okay, so equivalently, strong induction. Okay, in strong induction, the base case is P of 1. P of 1, same as P of 1. So equivalently, now I'm saying this is equivalent to the base case being P of 1, and the induction step, prove P of 1 and P of 2 and all the way up to and P of n implies P of n plus 1. Okay, because we get to assume P of 1 up to P of n. Okay, technically we need to prove P of 1 up to P of n plus 1, but P of 1 up to P of n came for free, so all we have to do is prove that this implies P of n plus 1. We just need to prove that this implies P of n plus 1, and that's strong induction. Okay, and this is strong induction. So, when you compare this to induction, same base case, easier implication to prove, and it basically establishes that P of n is true for all n greater than or equal to 1, same as induction. In fact, it is induction. It's just induction disguised as proving a much stronger claim. Okay, and we call this stronger induction because it's proving a much stronger claim. Okay, so we're going to use induction actually we're going to use strong induction, and I'll illustrate to you why we are going to need to use strong induction to prove the first part of the fundamental theorem of arithmetic. Okay, so, the idea behind induction, strong induction, all of those things is, to be able to conclude that a claim is true for a high value of n using the claim for lower values of n. Okay, so we're going to prove the first part of the theorem. So what is it saying? It's saying that every number is a product of primes. Okay, so let's see what it would take to convince you that, let's say, 2016 is a product of primes. So 2016 is a product of primes. Okay, and we're gonna use the induction approach, okay, which says, well, one way to convince you is that I show you 2016 as a product of numbers, okay, and then I have to prove to you that each of those numbers is prime. Okay, that looks relatively tough. That looks relatively tough. Okay. So, instead let's use the induction approach, which says that, my approach is going to be to somehow use the fact that the claim holds for smaller numbers to prove it for this large number. Okay. And so 2016 is equal to a product, and it may or may not be a product of primes. Okay. Well, so there are two cases. 2016 is either prime, in which case I'm done. Or 2016 is equal to a product, is what's called composite. Okay. And in this case, it turns out that 26, if it's prime, we're done. If it's composite, then we have a problem. Because how do we know that it's a product of things that are prime? So in this case, 2016 is equal to 32 times 63. Okay, so it's a product of two numbers, any two numbers, I don't care. Okay. And this is where the idea of induction comes in. So I'm trying to prove to you that 2016 is a product of primes. Okay. If I already know that 32 and 63 are products of primes, so if this is a product of primes, and this is a product of primes, then I'm done. And I don't need to know what those primes are. I just need to know that they're products of primes. I take this product of primes, multiply by this product of primes, and I have represented 2016 as a product of primes. So 2016 is a product of primes times a product of primes, which is a product of primes. Okay, and I'm done. So easy. Okay. And now the fact that I can convince you that 2016 is a product of primes using the fact that, some smaller numbers are products of primes is an immediate hint that induction is relevant. But now here's the problem. In regular induction, I need to use the fact that 2015 is a product of primes to prove that 2016 is a product of primes. So regular induction. I need to prove that 2015 is a product of primes, implies 2016. Okay, so this is analogous to the implications. It's basically the implication P of 2015 implies P of 2016. Okay, that's what I would need to prove. Okay, and that's very hard to prove. But strong induction, because in regular induction, I'm only allowed to assume 2015 is a product of primes in order to prove the claim for 2016. But in strong induction, I'm allowed to assume that every number below 2016 is a product of primes. In other words, the claim holds for every number below 2016. And that's when strong induction reveals its power. Because in proving 2016 is a product of primes, all I need is that it's a product of some smaller numbers, and the strong induction hypothesis tells me that no matter what those smaller numbers are, and you don't even need to tell me what they are, I know that it is true that any smaller numbers are products of primes. And that's what tells us that strong induction is the right approach to use here. Okay, so let me show you the full proof in all its details. So, the claim P of n is the claim that, and for n greater or equal to 2. P of n is the claim that, either n is prime or n is a product of primes. Sometimes we even can ignore the fact we don't add the clause n, either n is prime, because if n is prime, it's a product of one prime. Okay, so proof. And typically we just say by induction, okay, but I'll be specific here by strong induction. So the base case is P of 2, and that's prime. So check mark. Base case is check because it's prime. Okay, now I need to prove, so this is the base case. I need to prove the induction step. I need to prove that P of 2, so prove P of 2 and P of 3 and P of 4 and P of n implies P of n plus 1. That's the standard strong induction implication. Okay? And we're allowed to make this because at the time that we need to infer n plus 1, we know that all of these are true. So we might as well assume they're true. Okay? And make that implication. Okay, so prove this implication. So assume P of 2 and P of 3 and P of 4, P of n. Okay, so what is that assumption? Okay, because I'm trying to prove an implication. What this assumption is saying is 2 is a product of primes. It's a product of one prime. 3, 4, all the way up to n. They're all products of primes. Okay. Now consider n plus 1. It's either prime, in which case you're done. Check mark. Or it's composite. In the case that it's composite, n plus 1 is equal to, let's say, m times L. Okay. And I don't need to know anything about n times L except for the fact that they are less than n plus 1 because it's composite. Okay. And these are non-trivial factors. So they're between, they're greater or equal to 2 and less equal to n. So 2 less equal to m and L less equal to n. Okay. But in that case, I got to assume that whatever they are, as long as they're between 2 and n, they are products of primes. So this is a product of primes. And m is a product of primes. And L is a product of primes. And so that means that n plus 1 is a product of primes. You just take this product, multiply by that product, you get one bigger product of primes. Okay. And so I proved this implication, and that's the strong induction mechanics. So, therefore, we've proved that P of n plus 1 is true. Okay. And so by induction, P of n is true for all n greater or equal to 2. End of proof. We have proved the fundamental theorem of arithmetic part 1. We have proved that any number greater or equal to 2 is a product of primes. The primes are the atomic units for the numbers. Okay. Later on we'll prove that that product is unique up to reordering. Let's do another example with strong induction. By the way, this fundamental theorem of arithmetic is called a representation theorem because what does it do? It represents the integers using some other object. Okay. So it says that any integer greater than or equal to 2 can be represented as a product of primes. Okay, I'll end today's lecture with, I'm just going to give you 2 exercises. Okay, and you can solve both of these exercises using strong induction. So just to show you the variety, the amazing variety of applications of strong induction. And if you're having difficulty solving these problems, well, it's all in the book, in chapter 6, and I'll probably make a supplementary video on these 2 problems for those of you who are interested. Okay, so problem 1. Problem 1. Binary expansion. Binary expansion. Okay, so you have probably all seen binary expansions. Okay, so let me give you an example. For example, 18 is equal to, 2 to the 4 plus 2 to the 1. Okay, and so that has the binary expansion 1, 0, 0, 1, 0. So this is the 2 to the 0 place, this is the 2 to the 1 place, this is the 2 to the 2 place, this is the 2 to the 3, this is the 2 to the 4. And so what this compact notation, okay, is, it's saying 0 times 2 to the 0 plus 1 times 2 to the 1, that's that term, plus 0 times 2 to the 2, plus 0 times 2 to the 3, plus 1 times 2 to the 4, that's that term. Okay, and so we call this the binary representation of 18, or some of you might say 18 in binary. 18 in binary. Okay, and it may never have, you may have taken this as obvious, but what is a binary representation? Is it's exactly a representation of a number as a sum of distinct powers of 2. So we represent n as a sum. So represent, and hence it's called a representation. So you represent n as a sum of distinct powers of 2. Okay, interesting. And where the coefficients are either 0 or 1. Okay, so it's, in this case it's 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 4. Okay, and you might have taken this for granted, but an interesting question arises. Can every number n be represented in this way? So theorem, and just like the fundamental theorem of arithmetic, which is another example of a representation theorem in terms of primes, theorem, every n can be represented as a sum of distinct powers of 2. In fact, it can be represented in this way uniquely. So there's no other way to represent 18 as a sum of distinct powers of 2. That's also interesting. Okay, so just like the fundamental theorem of arithmetic, this says that the representation exists for every n, and it's also unique. Well, you can think about, you took this binary representation for granted. Well, how do you prove that you can always find a binary representation for a number? Okay, proof. Try to prove this by strong induction. And if you're having difficulty, it's in the text, and I'll probably make a supplementary video about this problem. It's too much to include in the lecture. We only have a finite time in the lecture. Okay, so read the text, or maybe watch the supplementary video if you're interested. Next, application of strong induction. So there's this, strong induction is very useful for, and induction in general is useful for analyzing, algorithms, recursive, greedy, dynamic programming. It's also it's also very powerful for analyzing games, especially strategic games. Okay, so there's a game called NIM, which means to steal or to pilfer. Okay? And I'm going to show you a very, very, very simplified version of NIM where you have 2 piles of coins, so pile 1 and pile 2. 2 piles of coins, 1, 2, let's say here I've got 5 coins, and here I've got 5 coins. So we're considering the case where the piles are equal. Okay, and at each turn, so you have 2 players, you have player 1 and player 2, and you take turns picking a pile and taking any number of coins from that pile. So if player 1 picks all the coins from pile 1, okay, so if player 1 picks all these coins, well, then player 1 immediately loses because player 2 will pick all the coins from the other pile, and the winner is the player who is the last to move, is the last to be able to take coins. So you win if you take the last coin. Okay, so clearly player 1 taking, all the coins from one pile at his first turn is going to be an immediate loss. Okay, so player 1 is not going to take all the coins. Okay, maybe he'll take 2. And now player 1 comes and takes 2, and now player 2 comes and has to decide how many coins to take and from which pile. So what will she do? Okay, so there's an interesting strategy which is called the equalization strategy for player 2. So if she equalizes the piles, okay, i.e. whatever player 1 does, she does the same thing to the other pile. So the equalization strategy. So player 2 does the same thing player 1 did, but to the other pile. So in this case, so player 1 took from pile 1, so and took 2 coins, so player 2 takes 2 coins from pile 1. 2 coins from pile 1. Okay, that's called the equalization strategy. Okay, and you see why it's called the equalization strategy, because it renders the piles equal again. Well, it turns out that this equalization strategy will guarantee that player 2 can win. So player 2 must win. No matter how many coins are in the 2 piles to start with. Okay, so I've just given you a strategy and I'm claiming that player 2 must win. Okay, but how do we know that? How do we prove that? You can use strong induction to prove that. Okay, so just to show you the range of applications of induction. Representation theorems, analyzing games of strategy. We'll see it in analyzing recursions, greedy algorithms, dynamic programming. I mean, wow! Induction. Get to know it early. Signing off.